As it turns out, infrared radiation causes vibrations to occur in certain molecules, not all molecules. Okay, and so what we have to do now is we have to model the chemical or the molecule in yet a different way now. We're going to look at molecules in yet a different way. This time we're modeling the bonds in a very unique way. This particular pictures, all these pictures are modeling carbon dioxide. So this would be the carbon and these would be the oxygens. And rather than modeling the bonds as a pair of electrons, or in this case 2 pairs of electrons, or as little dashes, in this case we're modeling the bonds as springs. Because as it turns out, atoms that are participating in a chemical bond are not static. They're not fixed in space, but rather they vibrate back and forth at a certain rate. Okay, so in all chemical bonds can be modeled also as springs. It's the next higher level of understanding of molecules. So we think of bonds as little springs. Okay, vibrating, oscillating back and forth. And there's different types of oscillations that can occur. Now, try to imagine, I don't know if you guys have ever held on to a slinky, but it's a pretty, a very stretchy spring. And if you're holding a slinky, there's 2 different things that you can do with it. You can stretch the spring and compress the spring back and forth, and that would be this kind of stretching motion. Or you can take the slinky in your hand and move it up and down, and that would be what we call bending motion. Okay, so you can do a stretching type of a spring action, or you can do a bending type of a spring action. And as it turns out, atoms that are involved in covalent bonds in molecules can undergo stretches. And depending on the number of atoms in a molecule, they may also be able to undergo a bend. As it turns out, molecules that have just 2 atoms are only capable of undergoing stretching. Molecules that have more than 2 atoms are capable of undergoing various stretching and bending. The stretching motion changes the bond length. Okay? The bond length is going to get further away and closer together, and further away and closer together. The bending action is going to change bond angles slightly. So although we modeled this as a linear molecule with a 180-degree bond angle, that bond angle changes slightly with the stretching, bending action. So this is a bend type of a vibration. This is a bend type of vibration that's going to change the bond angle from 180 to slightly less than 180. It doesn't bend all the way around, just slight bends. And then the stretching, this is a stretch. It's going to lengthen the bond angle, and this is what we call an asymmetric stretch. This side of the molecule stretching and making it longer, and this side of the molecule stretching and making this bond shorter. Okay, so this one's going to be shorter with the stretch. This is going to be longer with the stretch. Okay, so this gives us a more complicated but more realistic picture of molecules once again. We keep advancing our concept of molecules and the models that we use and the models that we need to employ to understand different physical and chemical phenomenon. So now we're recognizing that covalent bonds actually can be modeled as springs, and the bonds can undergo stretching and bending motion, and those types of bends and stretches are called vibrational motion. Okay? As it turns out, well, I'll get to that later. We'll just leave that now. There's different types of motions that molecules can undergo. Well, I'll tell you, yeah. For example, one is translational, and that's moving in space from one point to the other. And we think of like gases and liquids being able to move all around, translating from one place to another. So we call that translational motion. This is another type of motion called vibrational motion, in which the atoms are vibrating, stretching and bending relative to one another.